This is section 2.2, measuring the strength of evidence. So look through the objectives in the comic. So just a reminder of our official symbols. Our parameter, we said, is our population proportion, which we're going to call pi. And our statistic is our sample proportion, or p hat. Again, the pi is just the Greek letter for p. Let's see, so let's introduce terminology here. Remember, Dr. Bastian did that second experiment with the dolphins Doris and Buzz to see if they could communicate, and Buzz pushed the correct button only 16 out of 28 times. So we did this example in my video in our last set of notes. So there are two competing possibilities for Buzz's results, assuming that it's a good study and nothing else is happening. The first is what we're going to call the null hypothesis. You can think of it as the Dole hypothesis. That's usually just like by chance alone. The null is always like nothing interesting's happening. It's the same as it's always been. They're just guessing. It's very dull. Okay. So the null would be that Buzz is guessing, or that the true long run population probability of picking the correct button is 0.5 because he was guessing. We're going to use the specific notation. It's an H for hypothesis and a 0 for the null. I don't know why they picked a 0. But 0 for the null. And we'll say pi equals 0.5, that the population proportion is 0.5. Then what we call the alternative hypothesis is usually what the researchers are hoping to gather evidence to support. So it will always match the research question. So like in our case, the alternative hypothesis would be that Buzz is not guessing, that the probability of picking the correct button is better than guessing, that they're communicating somehow. So somehow it's better than 0.5. And we'll do an H with an A for alternative, and we'll say that pi is greater than 0.5. The probability of him getting the right button is better than guessing, so better than 0.5. So again, two competing explanations. They got lucky, random chance, which is the null, or there's something other than random chance at play, which is going to be our alternative. So we can usually simulate our outcomes assuming that it's chance alone, assuming that the null is true, and see how surprisingly observed results are. If they're too surprising, then the by chance alone, the null, is not plausible, and then we'll have evidence for our alternative. So if the null is not plausible, okay, the null is that by chance alone, then we will have evidence for the alternative. Then we'll use that 3S strategy that we learned about in our last section. So if you remember, we used the simulation to find that there was a 0.2938 probability that he could get his results 16 or more correct times out of 28 trials if he was just randomly guessing. That probability is called the p-value. Very famous, you'll see it in almost any research paper you ever read. There will be something about a p-value. So the p-value is the chance of seeing our statistic, or one more extreme, if the null is true, like if he was just randomly guessing. Okay, then we'll have a conclusion. Okay, so we decided that we don't have evidence that he is not guessing, which seems like a double negative, I know, but you always write the conclusion in terms of the alternative hypothesis, because the alternative hypothesis is what you are hoping to show. So in this case, we don't have evidence that they were communicating from that specific study. Okay, so the thing to remember, always write your conclusion in terms of the alternative. So here's some official information about tests of significance, which is what we've been doing. You just didn't know you've been doing it since the beginning of the semester. So the null hypothesis is the chance that the null model is correct. Okay, and it will always be an H with a 0, and it'll always be a pi equals. So it's always an equal sign. It's the Dole hypothesis. Nothing exciting is happening. Just guessing, if it's that type of thing. It's not always a guessing scenario, but like just guessing, nothing exciting is happening. The alternative hypothesis is what the researchers are hoping to show. So it will be an H, oh, sorry, that's the typo, H with an A there. And it'll be a pi, and it will either be like a pi is less than a specific number, or like less than something, or it'll be a pi is greater than something, okay? It will match the research question to decide if it's less than or greater than, and we'll get a lot of practice on that. You can see p-value is always going to be the probability of getting our results at least as extreme as the value of the statistic we actually got in the data if the null is true. So it always assumes that the null is true, or that the chance model is correct, or that they're just guessing. Okay. On the exams, you'll have to interpret the p-value. Always look for something that says the null is true, the chance model is correct, they're just guessing. Okay. To know which cell you're interested in, whether you want to look for like less than or greater than, you just look at the research question or that alternative hypothesis. Okay. You could also think about it as the proportion of simulated results at least as extreme as our actual statistic from the studies, because the simulation assumes the null is true. So to interpret the p-value, again, just to kind of take some things we already said and give them some more context or repeat them, the p-value takes into account the could have been outcomes, assuming that the null is true, that are as extreme or more extreme than the one we observed. Okay. So this provides a direct measure of our strength of evidence against the by chance alone, or the null model, okay, or the null hypothesis. So our p-value always gives us evidence against the null, okay, and allows for a standard comparable value for all scientific research studies. That's why every study will have a p-value, or just about every study. If they're doing any kind of test, they will have a p-value so that everyone can know how strong their evidence was. Okay. Smaller p-values mean the value of the observed statistic under the null model is more unlikely by chance alone. So smaller p-values are stronger evidence against the null. And so that means small p-values are stronger evidence for the alternative. So we're always looking for evidence against the null and for the alternative. So we like small p-values because they're stronger evidence for what we're hoping to show. Now your book has this guideline for evaluating strength of evidence from p-values. Every different textbook has these guidelines, but they're not set in stone. So different textbooks have different words that they use, different thresholds they use. Okay, so we're not concerned that you use this religiously. We're not concerned that you memorize it. Okay, really in this class, we're just always going to compare the p-value to 0.05 to decide if the null is plausible or not. Sometimes I might tell you to compare to 0.01 as a cutoff, but probably not. It's not very often. The reason why is some disciplines like medical journals, anytime they're doing research, they'll use 0.01 as a cutoff instead of 0.05. But for our class, we're just going to use 0.05 as a cutoff. So what that means, here's in this conclusion, if the p-value is less than 0.05, that means you have evidence against the null, which means you have evidence for the alternative, which is what you were hoping to show. But if the p-value is greater than 0.05, then you do not have evidence against the null. You do not have evidence for the alternative. And let's just remind ourselves, if the p-value is less than 0.05, that means it is statistically significant, which is just statisticians like to make up official words. Statistically significant just means the p-value is less than 0.05. If it's greater than 0.05, then you would say it is not statistically significant. Let's try an example. So researchers were interested in body odor as it relates to genetics, so they compared body odor between adult identical twins that were not living together. Okay, so they weren't just using the same laundry detergent, lived in the same house, and smelled the same. So they had female identical twins follow a complex hygiene regimen and were told not to come into contact with a variety of odors, anything super strong like garlic or smoke perfume, for 24 hours prior to the collection of their odors. They then attached pads to the upper part of their bodies and covered up with a cotton t-shirt before they went to bed. The pads were collected the next morning. Sniffers were then assigned to sniff a pad and try to match it with one of the 4 pads, and so one was from the identical twin and the other 3 were from non-relatives. So the 113 sniffers correctly matched 42 odors to that of the twin. Would you say that we have strong evidence the sniffers are more likely than just random chance to make a correct match? So let's go through our 6-step process. Step 1 is state the research question, which in this case would be, can people smell similarities in twins? Okay. Step 2 is design a study and collect data. So they already designed the study, they already collected the data too. But in practice, the researchers are going to come up with hypotheses before they ever collect any data. Okay. And we'll let pi be that long run proportion of times that a sniffer makes a correct match. So the null hypothesis is that the sniffers are just guessing randomly. So there's no similarities in smells, the genetics has nothing to do with the body odor, okay, just randomly guessing. Now, if they're randomly guessing, what should be our chance of getting one correct? Okay, so if you remember, there were 4 pads, okay, 1 was the correct, 3 were wrong. So if they're randomly guessing, it's actually going to be a 0.25 or 1/4 chance that they can get it correct if they're just guessing. This is different than most of what we've been doing with the 0.5. Okay. The alternative hypothesis is that the twins smell similar in a way. So if they were going to be smelling similar, they should be guessing or getting it correct more than just guessing, right? So wouldn't you think that their chance of getting it correct if they're not guessing should be greater than 0.25. And so that's what we mean by the research question, is figure out whether a greater than or less than would make more sense to you based on what you're expecting. Okay, so if they can actually tell that the twins smell similar, they should get more than 25% right. Okay, then you explore the data for something like this with proportions. It's really just the bar graph. You look at how many they got correct, how many they got incorrect. This one was the frequency. Okay, which is like the same thing as the count. So they were correct about like 41 times. It looks like they weren't correct as much as they were incorrect, but the question is, was it more than that 25%? So what proportion were correct in our sample? So in our sample, we'll do our p hat equals, and let's scroll back up, how many got it right? They were only right 42 times out of 113. So 42 out of 113 gives me 0.37. So that's my proportion that were correct. So now step 4, draw inferences beyond the data. We're going to have this 3-step process: statistic, simulate, and strength of evidence. Okay, so my statistic that I got was my p hat equals my 0.37, or as a count, it's 42 out of 113 correct. I shouldn't use the symbol, you might think it's a fraction. 42 out of 113 correct. So to simulate, we could use a spinner with what probability of success? Well, remember, we're assuming the null is true. So we assume the null is true, but we're just guessing. So if you go back, if you forgot, look back up at that null hypothesis. What did we say the probability was under the null? That it's 0.25. So when we simulate, it's very important that you put in the 0.25 as the probability of success and not your sample proportion of 0.37. So we'll use a 0.25 probability of success, and we have to do 113 times because that's how many actual observational units they had, and we count the successes, and then we repeat that thousands of times. So let's pull up our applet. Okay, so my probability of has to change to 0.25. We did something 113 times. 10,000 times, draw my samples. Okay, so we can look at the number of successes. They were correct 42 times. We still want it to be a greater than. Let's count that. Okay, so they were correct, or the chance of them getting 42 or more correct is 0.0003. 0.003. When I did it before, I got 0.002. Again, every simulation will be slightly different. That's just fine. Okay. Notice we did say that we wanted the 42 or more. So we're going to find that 42 or more, and that would be this area, everything over to the right. Now you'll notice the one that I put into your chart was actually only the proportion of successes. Okay. Which you can see proportion of successes looks exactly the same p-value. It doesn't matter if you have number of successes of the 42 or the proportion of successes of the 0.37. Okay. Either way, we're counting up how many times we could have gotten that 0.37 or more, or that 42 successes or more. Okay, so my probability though is 0.0020. So is it plausible? So my probability is 0.002. Is it plausible that the null hypothesis could be correct, that they're just guessing? Well, I would say no, because if they're just guessing, there's only 0.02 chance that they could get 42 or more, and they did get 42 or more. So I would say no. And are our results statistically significant? Yes, because it's less than 5%, or 0.05. And let's interpret that p-value. So to interpret our p-value, we'll say something like, if, and I like to always capitalize that because it's a big if they were just guessing, okay, or that's it, like if the null is true, okay, or if the chance is 25%, depending on like how you want to phrase it, any of those things. So if they were just guessing, or if the null is true, or if the chance is 25%, then there is a 0.002 chance that they could get at least 42 correct. that just does not seem plausible at all that they were just guessing. So then we formulate our conclusions. We're pretty sure they're not guessing. So we can say, like, we have lots of evidence, okay, a lot of evidence. So we have evidence that they are not guessing. Or, more importantly, what does your boss truly care about? We have evidence that the sniffers can identify twins by the smell better than just guessing. They weren't perfect. They only got 42 correct, but something is going on and it's better than just guessing. So, like, we have evidence that body odor is somehow linked to genetics. Okay, as far as to look back and ahead, they only looked at one pair of twins. Maybe this pair is an anomaly. They should look at more twins, or they only looked at a pair of female twins. Maybe females and males inherit body odor differently. So there's a lot of different studies they could do. Okay, but somehow we have evidence that at least for like this one set of twins, okay, that their body odor is somehow linked to their genetics. That it was not just guessing. So let's try another example with a null that is not pi equals 0.5. Okay, there is some more information we're still learning at the end. So make sure you don't cut out of this video. Okay, you will need the information after this as well, but this is just another example to clear up any confusion. So we were playing Settlers of Catan once, and we seem to be rolling far too many 12s. Because I'm a statistics teacher, I rolled my dice 500 times and counted the number of 12s to see if my dice were fair. I can tell you that if the dice are fair, you should get a 12 about 2.8% of the time. But I happen to get 19 out of 5 12s. So let's conduct a simulation to test whether my dice are fair or if I'm getting too many 12s. So first, what is the parameter? So you'll notice every question, and sometimes we ask you, every example we ask you different questions. This is to prepare you for the test. Sometimes like they'll ask you specific questions, and other times they'll ask you different questions. Okay, but you want to be able to be comfortable with all of it. Okay, so what is the parameter? It would be the long run proportion of 12s on the dice. Okay. And we don't know what it is. If we didn't know, we could call it pi. Okay. What is the statistic? It's my proportion of 12s in my sample. And specifically, what is it for this sample? We'll call it p hat, and I got 19 out of 500, which is 0.038. So what is my null hypothesis? My null hypothesis would be that the dice are fair, kind of that like status quo, nothing interesting happening, okay, or that my pi, let's use our official notation, my null hypothesis, I'll do an H with a 0. My null hypothesis is that my probability equals, what did I tell you should be if it's fair? I said if it's fair, it should be 2.8% of the time. So 0.028. Okay, dice are fair, nothing exciting is happening, pi equals 0.028. The alternative is that my dice are not fair, or specifically I get too many 12s. Okay, I apologize here. I kept going and apparently I didn't push resume. Okay, sometimes that does happen to me, so if you notice there are chunks of your video that are missing, please let me know. I will fix the videos. Okay, so in this case, I'll just kind of keep going, but I won't rewrite everything. So our alternative was that the dice are not fair, that we get too many 12s. Okay, and in that case, our alternative hypothesis would be that pi is greater than 0.208, because if I'm suspecting I'm getting too many 12s, I'm suspecting that maybe that proportion is greater than 2.8%. So we'll use our applet to calculate a p-value for the study. So the probability of heads is always whatever you have in your null hypothesis, so 0.028. Our number of tosses will be 500, because we rolled the dice 500 times. And the number of repetitions, I like to do 10,000. And we're going to count samples as extreme as, well, if you want to do proportions, you do greater than or equal to 0.038. If you want to do counts, you'll do greater than or equal to 19. So coming here, we need 0.028 as my probability. Okay. My sample size is 500. I want 10,000, so I draw my samples. And I want to count my successes as extreme as, what did I say, 19. Count. Oh. Okay, so here's some troubleshooting. It's saying, please enter a proportion between 0 and 1. It's because I tried to write 19 while I was on proportions. If I switch to number of successes, I can put in 19. If I want to do proportions, I can do 0.038. It will switch for me automatically. Okay. Either way, this p-value is 0.1148. Now you'll notice when I did it earlier, okay, when the video was off, it was 0.1091. So we'll just leave it as a 0.1091. You'll notice there is some difference because we are running a simulation, but we should be fairly close to each other. Okay, so my p-value is 0.1091. So if I want to interpret it, I say something like there is a 0.1091 chance of getting 19 or more 12s if the null is true, or that means like if the true proportion is 0.028. Okay. So is it plausible that the null hypothesis could be correct? Well, yes. If the null was true, there was about a 11% chance that we'd get what we got. That sounds completely believable. So the null could be plausible. Are my results statistically significant? Well, no, because my number is bigger than 0.05, so not statistically significant. Okay, what is your conclusion? So I like to think through all the different things that could be on the multiple choice test for you. Okay, so it could say things like, well, we don't have evidence against the null, because that's always what we're looking for. That means we don't have evidence for the alternative. But to your boss, your answer should always be in terms of the context of the problem. Like, we do not have evidence that the dice have too many 12s. Because it should always be in terms of your research question, always in terms of that alternative hypothesis. That, no, we didn't find evidence that the dice have too many 12s. Okay. So where is the null distribution centered? Okay. So let's continue our Sellers of Catan example. So remember, pi is 0.028, p hat is 0.03, and n equals 500. So here are the null distributions from the simulation. Okay. And we want to look at where they're actually centered. So if we're using proportion, let's do that one first. So at the proportion, where is it centered? It's centered at a mean of 0.028. So could you figure out a formula for what that center should be? Well, 0.028, that was pi. Okay, here my mean is 0.028. That seems really easy, okay? So if you use proportions, the center will always just be at pi, your hypothesized pi, the pi in the null hypothesis. Okay. But what about the count? Can you figure out what the count should be? How did they get a number of 13.983 or like 14? Well, they actually figured out, they said, well, if we run it 500 times and we're supposed to get 2.8% 12s, we can just do that 2.8% times 500. Okay, or let's try that. So 0.028 of 500 is 0.028 times 500 is 14. So that was just pi times n. So my center will always be at pi times n. And here's the little box. You don't have to memorize this. If it asks you where the center should be, just bring up the applet and see what this applet says is the center. Okay. So you can come back to this applet and you can click on summary statistics and it will tell you the mean is 0.028 and you know it's centered at 0.028. And if you want the count instead, click on that and it'll tell you, oh, it's like 14. Okay. But you can also use these formulas if you wish. So another example, researchers wanted to test the hypothesis that living in the country is better for your lungs than living in a city. To eliminate the possible variation due to genetic differences, they located 7 pairs of identical twins with one member of each twin living in the country, the other in a city. For each person, they measured the percentage of inhaled tracer particles remaining in the lungs after 1 hour. The higher the percentage, the less healthy the lungs. They found that for 6 out of 7 pairs, the one in the country had healthier lungs. So what is the parameter? Well, you can say something like the proportion of all twins where the country one was healthier. And that would be pi. We just don't know what number it is. What is the statistic? Well, that would be the proportion in the sample where the country one is healthier. And in our study, it was p hat is 6/7 or 0.857. The null hypothesis will be no difference, that pi equals 0.5. And the alternative hypothesis is that more are healthy in the country. So that would mean like pi has to be greater than 0.5. So let's use an applet. Okay. So if we were to use proportion as the statistic, where do you think the null distribution should be centered? Well, it should be at this pi equals 0.5. Okay. And if we use count, well, if you think about it, if there's 7 people and under the null, like it should just be half and half, well, half of 7 is 3.5, or pi times n is 0.5 times 7, or 3.5. So that's where it should be centered if you use count. Let's see, what is the p-value? Let's bring it up. We'll probably get something slightly different because I already did this one earlier. Okay, so my probability of success is 0.5. My sample size is 7. Okay. Let's draw our samples, and I want to count anything as extreme as greater than or equal to 6. Okay. So it looks like that gave me 0.0618. Earlier I got 0.0643. Again, simulations aren't exact because you get different results each time. So to interpret that p-value, if the null is true, Okay, you can put that at the beginning or end of your sentence. Or in other words, if there's no difference in country versus city, then there's a 6.43% chance, I changed it to percentage, doesn't matter, you can do it either way, that we could get 6 or more healthier in the country. Well, that seems pretty plausible. That's over 5%. So yes, my null seems plausible. And we're not statistically significant because we're more than 5%. So what is your conclusion? Well, we said the null is plausible. That means we have no evidence against the null. We have no evidence for the alternative. Or to tell our boss, we do not have evidence that the lungs are healthier in the country based on this study. Now, were we really close? Is 6% really close to 5%? Yes, we're really close. So they should probably just go do another study, go try again, get a bigger sample size, and they might actually find evidence that the lungs are healthier in the country. But we didn't find that much evidence here, but we did only have a sample size of 7. So let's suppose another study also looked at twins and their lung quality, but they got a p-value of 0.002. So which study found more evidence that living in the country is better for your lungs? Okay. Well, the second study actually did get a small p-value, so they'd actually say that they found evidence, and we didn't find evidence. But in general, smaller p-values are always more evidence against the null. Okay, or smaller p-values are more evidence for the alternative, which is what you were hoping to show. Okay, so a p-value of 0.002 is, much more evidence that the country is better for your lungs. Okay, smaller p-values mean more evidence.